Great. Welcome to CS159, Advanced Topics in Machine Learning, Data-Driven Algorithms Design. Today, it's a great pleasure to have my PhD student, Joe Marino, give the lecture on amortized inference and deep generative models. This topic is closely related to his thesis work, and he'll be giving an overview of this area. Take it away, Joe.
Great, thanks, Isong. It's really a pleasure to be able to give this talk. It's kind of my main area of research. I'm excited to share it with you all. I do have one thing to apologize for, which is that I have a lot of peacocks in my neighborhood, unfortunately. So if you hear any disturbance in the audio, I apologize for that. So we're going to be talking about amortized inference and deep generative models. If you don't know what amortized means, we'll get into that. But yeah, we're going to be looking at basically variational autoencoders. If you've heard of those, that's generally the setting that we're going to be working with. Okay. So just a quick outline of what I'm going to be talking about. We're going to go through some background just on what is a deep generative model, what is inference, what are all these concepts that we're talking about, and then what are variational autoencoders and why are they an instance of this meta-optimization or learned optimization that we've been talking about in this course. And then I'm going to talk specifically about some of the work that I've done in trying to extend these optimizers to kind of a more flexible class. And then go through some closing remarks, just some things that people have kind of like overlooked somewhat, and some interesting directions that maybe you might want to explore further. So just to give like a motivation of where we're coming from, the general kind of scientific term for these class of models are sometimes referred to as forward models. So what's a forward model? So in science, generally, we have some observations that we've obtained from the world, and we want to try to model those and try to understand what's the mechanism that's generating those observations. And a forward model is one way of thinking about this kind of formalism, where we have some model of how an observation is generated. So that might be that we think that there's some phenomenon called a black hole out there and it has some brightness. If you recognize this image, then good for you. But what we really have are these frequencies that we're getting from these radio telescopes. And so there's some model that we have that describes how that brightness translates into these frequencies that we're actually observing. But what we really want to be able to do is solve this inverse problem. So we'd like to be able to invert this forward model in order to obtain that underlying state. So we have these radio frequencies here, and we'd like to be able to go back and say, okay, what was the black hole brightness that generated these observations that we're seeing? So we'd like to get those frequencies and do this inversion process, which I'm denoting with this dotted arrow here. So that's kind of like the general paradigm of where we're coming from here, is we have some model and we'd like to be able to invert it back to this underlying state. So the general like mathematical way of attacking this would be through what's called a latent variable model. So we have this kind of plate notation formalism for it, where we have this latent variable z here, which is denoted with a blank circle, and then we have these arrows which are denoting this generation process. So z here is generating this observed variable x, which is this filled in circle, and we might have some global parameters theta that describe that relationship, and then we might also have n particular examples of this generation. So we'll define a probabilistic model over this process, and that model is defined by this joint distribution. So this is a joint distribution over the variable x and z, and that's just equal to the chain rule of probability, this conditional likelihood of how does some particular latent state give rise to the observations that we're seeing, and what is the prior that we have over the latent state. So I didn't really get into it in that black hole example, but in those examples, you actually need to have some idea of what you're expecting to see. You have to have some prior estimate over what that latent space might be. It might be a uniform distribution, it might be some other distribution, but you need to have some prior expectation. And the way that we would go about kind of verifying how well does our model actually fit the data is by evaluating this marginal likelihood here. So this is kind of like, okay, for all of the latent states here, we're integrating over all the possible underlying settings that could exist. And so, you know, that's giving us this marginal of a particular data example. But what we'd like to actually do as well is able to go back and do this inverse problem that we talked about. And so we're gonna refer to that as inference, so probabilistic inference. And that corresponds to estimating this posterior distribution. So up here, we talked about we have the joint distribution, we have this conditional of x given z, but down here, we actually like to go back and say, okay, given an x, what was our z? So what is the probability of z given x? And we see that evaluating this posterior distribution involves evaluating this marginal likelihood, and that marginal likelihood, if we have a lot of underlying latent states, or if our model is really complex, we can't actually evaluate this, this integral here. So that integral is just fundamentally intractable. And so we're gonna have to resort to some other techniques. So this is just hashing that out in kind of from this perspective of maximum likelihood inference or estimation, where what we'd like to be able to do also is actually train our model. And that involves maximizing the likelihood of the observed data that we have under our model. So we have some expectation over the data that we're observing. So these are observations that we're obtaining from the world, from the true data distribution, and we'd like to maximize the log probability of those examples under our parameterized model. So the typical way we'd go about doing this is by approximating this expectation with just an average over the data examples that we have. We don't actually have access to the true data distribution. So xi here is the ith example of observations that we have. And again, evaluating this marginal likelihood here corresponds to evaluating this integral, and that integral is generally intractable. So you can construct particular models where you have particular types of distributions, particular types of mappings. So if you're familiar with linear Gaussian models, of which you can derive things like probabilistic PCA, you can perform exact inference. You can actually kind of get around this intractable integral in those cases, but in general, you cannot. You're gonna have to confront this integral in some way. So we're gonna have to resort to these approximation techniques, as I alluded to. And if anyone has any questions, feel free to stop me on this. It's not totally essential that you understand this generative modeling aspect of it, but it can be helpful to get an intuition for where we're going. So one of the most popular ways of attacking this approximation is through what's called variational inference. So variational inference, the key idea there is that we can't evaluate this true posterior distribution. We can't actually do this inverse problem in the way that we really mathematically would like to. So what we're gonna do instead is we're gonna propose an approximate posterior distribution, which is denoted as Q here. So Q of z given x. And what that's gonna allow us to do is this nice thing where we can actually we can lower bound the log marginal likelihood. So remember, we wanted to be able to evaluate this thing. And so now we can at least form a bound on it. And if we can push that bound up, then we can hopefully push up the actual marginal likelihood. And the nice thing about this as well is that by actually pushing up this bound, we get this approximate posterior distribution, which doesn't correspond mathematically exactly to the thing that we actually wanted, that true posterior distribution. But it gets us pretty close. And for the purposes of actually training these models, sometimes it's totally sufficient. So in particular, what does this bound actually look like? If you haven't seen this before, it can be a little difficult to get kind of the full intuition for it. But just at a very high level, what you should take away from this is that we have one term here, which is kind of gauging how well you're reconstructing the data. So this is saying, in expectation under your approximate estimate of what the latent variable actually is, how much likelihood are you assigning to the observation that you have? So this is kind of like, if I have some estimate of what the latent state is, how well can I reconstruct in some way what that observation is? And this second term here is saying, okay, how far are you really away from your prior estimate? So this is, in a sense, doing some type of regularization of saying, don't just overfit to the data examples you have. You have to make this somehow consistent with the model of the world that you have. And so this is kind of this natural, like, Bayesian idea of let's trade off between fitting these observations that we have, but also respecting these prior expectations that we had coming into this problem. And we're gonna, throughout this talk, represent this in this kind of a way. This is just a notation that I tend to use for kind of a shorthand. And so what does this set of dots and arrow represent? So up here, we have the latent space. So this is the Z in this kind of formulation. So these larger circles with the black rings around them are corresponding to distributions here. So this is our prior, and this blue dot is our approximate posterior. This red dot is the second term in the objective. So this is this log ratio. And then down here we have the observed variable. So this green dot is representing our conditional likelihood, P of x given z. And then the gray dot here is representing our actual data example that we have from the data distribution. And then finally, the red dot is representing the first term here in this objective. So the kind of way you should think about this is some type of computation graph consisting of probability distributions, conditional mappings, and these red dots denoting kind of the objective terms. So you think of that as like some type of error, some type of thing that we want to maximize in this case, or minimize in the kind of negative case. So this is the kind of notation that we're going to use throughout this. And the way that you go about training this model is through what's called the variational expectation maximization algorithm. So if you're familiar with kind of classical probabilistic formulations of these models and the way you train them, there's this technique called the expectation maximization algorithm. This is just kind of the generalization of that to this variational case where you can't actually fully do the expectation step. And so the way that goes is something like this, where what we're going to do for one particular kind of iteration or step of this algorithm is we're going to sample some data examples from the data distribution. So we're going to sample this mini batch consisting of M examples. So here we have X1, again, this is the first example, the second example, up through XM, the mth example in our mini batch. And we're going to line up all of these examples here. And what we're going to do is kind of hook up our model to these examples, and we're going to try to maximize this lower bound that we talked about with respect to these distributions that we're estimating, these approximate posterior distributions. And this is this variational E step or expectation step. And so that's just saying, I want to find the distributions, kind of solve these inverse problems for each of the examples that I have in my mini batch. So I want to find these blue dots. And then after that, once I've estimated those dots, I've kind of tightened my bound as far as I can. Then what I'm going to do is I'm going to actually maximize this average over my mini batch of these bounds with respect to my model parameters theta. So this is this M step. And just to step back, this E step is generally referred to like as the inference step, and this M step is the learning step. So you can think of this as like you want to infer what's the state of the world, and then based on that inferred state, you want to adjust your model to kind of make the observation that you have more likely. You want to learn kind of a better model of the world. So this is kind of the whole algorithm here. But what we notice is that for every single data example, we have to solve this optimization problem here. This E step inference optimization problem. And in general, that can be quite expensive. So you know, for every single data example, and every iteration of training, if we're not, you know, sneaky about it, we have to solve this optimization problem which in general could require, hundreds of gradient steps or some type of gradient-free optimization, which could require a lot of steps as well. So a lot of like the innovations in this idea revolve around kind of making this E-step less computationally expensive. And that's kind of the main idea behind an autoencoder. Although it's not always motivated from this perspective, what an autoencoder is doing is what's called amortized optimization. And so amortization is this term that was kind of borrowed from the finance literature for some reason, but it's a similar idea. And so in amortization, in finance, it refers to kind of like spreading out a cost over a series of installments. It's a similar idea in the optimization sense, where what we're trying to do is, instead of doing these separate individual optimizations, what we'd like to do is spread out the cost of optimization by using a learned model. So we're actually going to learn a model that allows us to do optimization more efficiently by sharing it across different runs of this optimization. And so the idea of an autoencoder, which it goes without saying, but autoencoder literally means self-encoder, so you're encoding yourself, is to learn to directly estimate this approximate posterior distribution, Q of z given x, as this conditional mapping from x. So we talked, in our generative model, we had these conditional mappings that involved z to x, and it was parameterized just as this direct mapping. Here we're going to try to like directly learn the inverse mapping of Q of z given x. And so by considering this as a parameterized mapping, we're going to write this with a subscript phi here, just to denote that there are some underlying parameters phi here which are parameterizing this mapping. And so in the kind of notation, or this kind of diagram that we saw before, I'm going to represent this as this dotted or dashed arrow here, going from our observation x to this approximate posterior, this blue dot. And we can also write this in this kind of format. And you see where I've just kind of copied over this observation dot. We see that we have exactly this auto-encoding setup where we take our observation, we encode it, we do some regularization in this latent space, we decode, get a conditional likelihood, and then we see how well that reconstructs the example that we have. So in a sense, it's really just doing some type of compression at the end of the day, and that's really all it is. But the kind of cool thing is that a lot of the autoencoder literature wasn't really motivated necessarily from this perspective of trying to do inference, but once you really kind of like formalize it in that way, you realize that what an encoder is doing is this form of meta optimization. So we're actually trying to learn how to infer these latent estimates, and that's precisely the kind of idea of this class is how can we perform optimization more efficiently in some way, or how can we do some task by utilizing some domain knowledge to speed up the task itself. And so now we'll get into kind of how we might go about actually performing that. So this is going to be the more technical part of the talk. I wouldn't say it's absolutely essential that you totally internalize all of it, but I would say that these are really important concepts that just come up again and again if you're trying to estimate distributions. And so I think they're very general tools, and they're worth kind of at least having some sense of. So I would recommend going back through the slides if you have a chance later on to think about them a bit more. And so if we want to learn these encoder networks, if we want to perform this meta optimization in some way, we need some way of estimating kind of how to improve our encoder. So we need some way of estimating this gradient of this lower bound that we're trying to optimize with respect to the parameters of our encoder. So we needed some way of doing this meta optimization. And you can visualize this as like, we want to be able to get gradients from these red dots back into this dashed line over here. And that's, we can do that through chain rule, but because we're dealing with distributions, it can be a bit tough. It's because here we want to optimize with respect to phi, these parameters that are parameterizing our approximate posterior. But we see that approximate posterior actually appears in this expectation. It appears within the expectation, but it appears as the thing we're taking the expectation according to. And that's something that's is difficult to optimize that type of form of objective, where you're actually optimizing the thing that you're sampling from. Because sampling is, in general, is non-differentiable procedure. So this is, this problem that requires what's called stochastic gradient estimation. And there's a paper by John Schulman from 2016 and colleagues that discusses this in kind of this nice kind of framework. So I really recommend, if you're interested in looking into this, there's a nice paper by Schulman that goes through this. But this is kind of the general paradigm, where we have some parameters that we want to optimize. These are meta-optimizer parameters. And we have this distribution over this variable here, and we'd like to optimize it with respect to some downstream target down here. So this is the gradient we want to optimize. So here, like the bound, or what's inside of the bound would be this f, and then this expectation again is with respect to the thing that we're trying to optimize. So we have some options for how we could go about approaching this. So we can't just directly bring this expectation inside of this, or we can't directly bring the gradient inside of the expectation. We can't directly just apply the gradient to the thing we're taking the expectation over. But one idea would be, okay, we were talking about distributions up to this point. Let's just go with a point estimate. Let's just have a single point that defines our estimate in the latent space. And so we could represent this as this kind of delta function where we only return the z hat parameterized by phi. So this is like kind of a classical autoencoder where you just return a single point in the latent space. And when we do that, because Q is just a single point, this expectation just turns into a single point that we're estimating, in which case it goes away and we're just estimating the gradient at that one point. So that would be one way to get around this, is just say, okay, forget about distributions, let's just have a single point. But if you haven't been able to tell up until this point, that's a very inexpressive way of parameterizing the model. You're not getting the stochasticity, which allows you to consider these multiple options, which really allows you to explore kind of the space of your model. And so in general, it's not going to allow you to train a very expressive model. And so another way to approach this would be to use what's called the score function estimator. And in reinforcement learning, this is called the reinforce estimator, or the policy gradient estimator. So this is a thing that comes up over and over again, which is just, it's a mathematical trick. I would encourage you, if you're interested, go look up, there's a nice kind of simple set of steps to drive this. But basically, if you have a gradient that you're trying to take of an expectation, you can convert it into this form where you have the downstream kind of target that you have, and then you have this gradient of the log probability of the thing you're taking the expectation under. So this is a very general technique. It works for any probability distribution, although the kind of issue with it is that the gradients that you get out of this tend to be very high variance. So depending on what sample you draw of Z in this expectation, you're gonna get a huge range of possible gradients. They will be unbiased estimates of the gradient, but you're gonna have to draw a lot of samples of Z in order to get a good estimate for most problems. But it is possible to use this in this autoencoder paradigm. So there's these papers from kind of before really the variational autoencoder came to the forefront, called like Enville, Darn, UProp, and Vimco. There's some other ones as well, where you are using this score function or reinforce estimator. So it is possible to use this. But the kind of main technical innovation of the variational autoencoder is using a different type of gradient estimator. And that's in particular this reparameterization gradient estimator. And so again, we have this stochastic gradient estimation problem that we're trying to tackle here. And what we're going to do is apply this other technique called the reparameterization trick. It's also sometimes referred to as the pathwise derivative estimator. So the key idea, and it's going to sound stupidly simple once you see it, you've probably already seen it, but the key idea is just we're going to reparameterize this distribution as, instead of being the stochastic function, we're going to let it be a deterministic function, which is a function of an auxiliary random variable epsilon here. And now we can just express z not as a sampling operation, but as this deterministic operation here. So graphically, that corresponds to this kind of a setup where you have this phi, which is, again, going into give you z, but now z is this deterministic node, which is giving you f. And so you have this randomness that's being injected kind of into z, and now by turning z into this deterministic node, you can actually backprop through all the way back to phi. So the idea is to express the gradient in this way, so you can convert this expectation over this q into an expectation over this auxiliary random variable, and that allows you to bring this gradient operator inside of the expectation. And then, so the canonical example would be this Gaussian setup where you're sampling a Gaussian random variable with mean mu, diagonal covariance here, and you reparameterize that sampling operation as this deterministic operation consisting of just this affine transform where you take mu, you add sigma times some random standard Gaussian noise, and that gives you out this z, which now is deterministically expressed in terms of mu and sigma, but it has this randomness that's coming in, and so z actually does take this Gaussian form as a result. And so that's the key idea behind the variational autoencoder, is that we're going to combine a latent variable model parameterized with deep networks with variational inference, have this direct encoder that we talked about, this meta optimizer, and use a reparameterized Gaussian as this approximate posterior. So mechanistically, again, we have this setup of a observation being fed into our approximate posterior. We have this regularization, we have this reconstruction. And if you pop the hood on what's going on here, you have this deep network that's giving you your encoder here. Inside of the latent space, you have this reparameterization that's going on. So let's just quickly go through this. So you have the output of your encoder is giving you mu and sigma here. You're taking sigma, you're element-wise multiplying it against epsilon, adding it to mu, and that's giving you z. So that's kind of the circuit that's going on inside here. And then at the decoder side, it's just another neural network over here. And so the nice thing is that you see that you can backprop through a neural network. You can backprop through all of these nodes here because you don't have any random variables within the approximate posterior. So you have these lines along which you can backprop, and then you can backprop through your encoder. So you can backprop through the entire thing, and that allows you to train this very efficiently. And so where is this kind of allowed us to go? Like these encoder networks really have been a game changer, I would say. And so kind of the first VAE papers, it was actually a pair of papers from late 2013, early 2014. And this is one of the first VAE papers from Danilo Resende and colleagues, where they're looking at just patches of CFAR10 and they're trying to model these with this very limited VAE. But over the years, by scaling up these deep networks within here, this was some of the first, if not the first, work to actually look at generative modeling of natural images using deep networks. And then, just a couple years later, people were generating much more diverse. This is also CFAR10 diverse samples here. And, the samples have gotten fairly good for these models, I would say, to the point where, this isn't strictly a VAE as we've talked about it. This particular paper has discrete latent variables, but it's a similar kind of idea of autoencoding. And they're generating these samples of these like 256 by 256 images that are pretty realistic at this point. And so on the, it hasn't just been this reparameterization trick. By having these models that can be trained in this flexible way, it's really allowed for just a flourishing of new techniques to be developed. So I think the most prominent of those is this idea of normalizing flows. So actually using this more flexible approximate posterior. We're not going to get into that in this lecture, but that's a really cool idea that came out of this. Applying these models within like a dynamical setting, which we'll get into a bit later. Looking at actual hierarchical models, so having some hierarchical structure to the model and actually being able to train that using this encoder kind of paradigm. And then, a number of kind of architectural considerations have been made where, you have this decoder and then you have this very flexible autoregressive pixel CNN output layer. And so being able to actually train all of these models requires having this encoder type of setup where you can actually like be able to estimate these approximate posteriors in order to be able to train the model itself. So, we've made a lot of progress, but it isn't all perfect. So this amortized or meta-optimized inference has a couple of issues, which we'll get into here. So one issue is what's called this amortization gap. So this is a paper from this guy Kremer from 2018 and colleagues, and they did this cool thing where up until this point, people had kind of said, okay, we have an encoder network, we have a decoder network, we'll just set them up and hope it works for the best. And so they actually looked and said, okay, what would be the true posterior distribution? None of this approximation business. Let's set up some models and look at what is the true posterior distribution for this model. And so they're visualizing this for like a 2D space, what that actually looks like. And then they go in, they have their encoder network and they estimate what is this factorized Gaussian that we've been looking at. What is kind of the output of this encoder network? And we see that, okay, it's outputting these Gaussians here. Some of them are pretty bad. Like this one isn't even overlapped well with the distribution. This one's just kind of on one of them, but not totally. This one's a bit misaligned, this A example here. And so if you actually go in and properly, perform the optimization, either using gradient-based methods or, just doing some like enumerative search in some way, you can see that the optimal factorized Gaussian is not the same as the amortized factorized Gaussian. So that says that our amortization, you see like, this optimal Gaussian, for example, A, is more aligned with the true posterior than the amortized Gaussian. And that's saying that amortization is giving us some cost. So we're not getting as good of estimates as we kind of would hope that we would get by using these encoder networks. And so this is kind of like some troubling bit of news, but it was kind of a very interesting idea because people hadn't really thought about what are the costs incurred by using this encoder style network. And so in my work, I also visualize this as well, where you can directly visualize the optimization surface. And so this is, again, a 2D latent space. And so this blue dashed line is showing gradient-based inference, trying to optimize the latent estimate. And you see that it's initialized here at 0, 0, and it's kind of moving around the landscape and eventually gets pretty close to this red dot. So here's a zoomed in version of that, where you get pretty close to this global maximum through gradient ascent here. And so, and this kind of turquoise diamond is showing what the output of an amortized inference network is giving you. So it's giving you something that's pretty close to the true estimate, or like the optimal estimate. But it's not as close as what you would get through more of this direct optimization technique. And so we're incurring, again, some cost by using these encoder networks that wasn't totally obvious to us before. And so another issue that you come up against with these models is that, oftentimes you want to be able to construct these more structured models. So again, I alluded to like hierarchical models with various dependencies inside of them. You might want some kind of like dynamical model where you have these dependencies now across time. And it's, you might think, okay, we saw this in the VAE, we'll just hook up an encoder network that gives us, takes as input the observation and outputs the estimate of the approximate posterior. But you realize that actually you can't directly account for your latent dependencies with these direct encoder methods. So naively, you can't. You can construct ways of doing that, and there have been some technical innovations on that side. But you have to be a bit careful if you're just thinking in terms of, oh, it's an encoder network that encodes data examples. It's not that simple, and you're going to run into some issues if you just blindly apply encoder network without thinking about the structure of your problem. And again, the issue here is that, so for instance, in these hierarchical models, the lowest level of latent variables depends on those higher levels. But if you're just encoding from the observation, you have no way of accounting for what is your top-down input that you're getting. So you have no way of accounting for your priors in these cases. And that's an issue that you see. And then I think one of the last things I want to touch on is just that up until this point, we've kind of thought about an encoder network just giving you one estimate of what the approximate posterior would be. But there could be cases where there are multiple equally valid estimates. And if you just have an encoder network that goes from X to this distribution, you have no way of getting anything other than a single estimate. And again, there are ways of getting around that by like adding randomness within your encoder network. But naively, if you just hook up an encoder network, you're only going to get a single estimate out for a particular data example. And that can be an issue in certain models, not in all models, but in certain models, where in this example from Greff and colleagues from last year, they looked at a model of objects where there's kind of multiple interpretations that are equally valid here. And those interpretations can send you into various parts of the latent space. And so if you have just a direct encoder, you can't capture all of these different modes of the latent space. And so, inspired by some of these issues and kind of work that was done, around the same time and a little bit before my work, I was thinking a lot about, okay, how can we improve these inference optimization techniques while still retaining the benefits of amortization? And so kind of a huge aha moment was looking at more of the classical literature. So if you look at these classical control and state estimation techniques, going back to like Norbert Wiener, where you have these early control systems, or like the Kalman filter, or even looking at these kind of predictive coding types of setups where you have these models of brain function, what you find is that you have these error signals throughout. And so you're thinking, okay, why would we use an error signal? And it's precisely because those error signals denote the information that your current estimate is missing. And so you're using those error signals to guide how to update your estimate iteratively. And so this is kind of this common paradigm that you find all throughout kind of these classical techniques. And this got me thinking, okay, how can we use something more in line with this style of inference? And I'm by far not the first person to think along these terms. I was heavily inspired by this work from Tutsky and Max Welling, where they're doing inference using a model that takes in gradients to output updated estimates. Here, this is in like a denoising setting. You know, and as you've probably seen in this class already, you know, there's a lot of work on using gradients as inputs to models for updating parameter estimates. And even within the VAE literature, you know, there's been some push toward this iterative refinement of like, let's use an encoder network, but then we'll do a number of refinements along the way after the fact to kind of improve our estimate. So my work is by far not the only work to look at this, but I approach this in a slightly different way than some of these other works. And I'm not going to go super heavily into the details, but this is the general setup of this approach that I took, where we're going to say, okay, lambda, bold-faced lambda here are the distribution parameters of our approximate posterior distribution. So in this case, it'd be like this set of mean and standard deviation. And we're going to set up this iterative inference model where we somehow take in a function of our objective terms, so the terms that we want to optimize. These are the only terms we really should care about, and try to update our estimate based on those terms. So one form of doing this, which is kind of more in line with what people had previously done, was or is to use a function. So this is our inference function that our meta optimizer that we're trying to learn, which takes in our current estimate and takes in the gradient at our current estimate of the objective. So these are kind of like the only signals we need to know. If you think about like gradient descent, what does gradient descent do? It takes in your current estimate, your gradient, and updates your current estimate. And another form, which was inspired by predictive coding, but is, you know, a result of actually looking at the gradients and seeing what are the terms that you actually need to perform inference, is to take in your current estimate and these two error terms. This is the error in your observation and the error in your latent space, and those are defined in this way. I'm not going to get into exactly why, you know, you need these particular ones. This is for the Gaussian case, but this is another valid format of setting up these models as well. So this is kind of two ways of thinking about parameterizing these kind of new, hopefully more flexible encoder networks that can solve some of the problems that we looked at before. And so one way of kind of looking at how these networks are actually performing optimization is to, again, visualize in this 2D space. And so it's maybe a bit difficult to see, but there's a turquoise set of turquoise diamonds here with a dashed line between them. And those are visualizing the optimization trajectory of an iterative inference model. And then, again, this is a zoomed in, on the right is a zoomed in version of the optimization objective near the maximum. And you see that, you know, this inference model is making huge jumps in the latent landscape. And then once it gets progressively closer to the global maximum, it's taking these smaller and smaller steps. So it does appear to have learned something like gradient ascent here. But hopefully, you know, compared with kind of classical gradient-based techniques, it's much more efficient by getting you pretty close even within a couple of steps, rather than having to make this huge traversal of the landscape. Another way to visualize kind of what's going on is to look at the reconstructions. Hopefully the reconstructions are improving over successive inference iterations as we kind of optimize our objective more and more. So here on the left is showing kind of the initial decoding from just a prior of our model. And we're trying to reconstruct these examples shown in this column on the right. And so you see that over successive inference iterations here, going from left to right, we get progressively closer and closer toward the data example that we're trying to reconstruct. So you can think of this as like you take an initial guess, you look at how off your guess was, you update your estimate, you do this multiple times, and eventually you get closer and closer toward kind of the reconstructing the data quite well. And so I looked at this for other data sets like OmniGlot, the Street View House Numbers data set, and the CFAR10 data set. And you see a similar phenomenon, although with qualitatively some slight differences along the way, depending on the model. But you see this progression of like it's becoming closer and closer to the reconstruction over inference iterations. And then another thing you can also do is just to look directly quantitatively at the elbow, this lower bound that we're trying to maximize. So if you compare these iterative inference models with more kind of classical gradient-based optimization techniques, you do see that they are much more efficient, which is really nice if you're repeating this inference optimization over and over and over again for training. It's nice to really make that as efficient as possible in order to speed up training. So here, this is showing in terms of inference iterations. It's also faster in terms of walk clock time. And then I think one of the last plots I wanted to show is just, this is another way, yet another way of looking at inference optimization, is showing over the course of training, each line here is the magnitude of the gradient over successive inference iterations averaged across the validation set here. And so you see that, you know, throughout training, it's learning to basically, it's starting off with these high gradient magnitudes, so really steep gradients, and getting down to a point where the gradient is much shallower. So you're hopefully reaching these optimized estimates as well as possible. And you see that, you know, the landscape changes somewhat throughout training. And then another kind of way I looked at a few different forms of these models. And you see that, you know, by increasing the number of inference iterations during training, so like having a longer kind of horizon over which you're optimizing, tends to improve the performance of the model itself. And in all cases, I found that this ended up performing better than these kind of direct encoder networks of a similar architecture, which was kind of encouraging to see, although it is fair to say that, you know, if you just need a rough estimate, you know, you can go with these direct encoder methods, and they will get the job done most of the time. And final point here is just that these iterative inference networks, so this paper by Greff and colleagues, they actually did use iterative inference there, and so they found that that was pretty essential for being able to train with these kind of multiple optima within the latent space, which is a nice added benefit that I hadn't really anticipated, actually. And so one nice thing about these models is that we talked about how, you know, okay, with these structured models, it can be a bit difficult to actually think about how to set up the proper inference network. But with iterative inference models, you know, these dotted lines look a bit complicated, but they are totally defined in terms of the gradient. So the structure of your model determines what your gradients are, and those gradients determine what the inference process is. So the nice thing here is that you really don't even have to think about setting up your inference model. It's just a one form of model for everything. And so that's kind of this added benefit. And you see, you know, the same thing in the temporal domain, where you basically let your model and the objective terms that are in your model define the inference process. So again, the arrows look a bit complicated, but it's all totally defined by the gradients themselves, not by kind of the engineer that has to think up what would be the right inference structure for doing this. And this kind of motivated the next line of work, looking at this particular case of what's called filtering inference. So this is in this dynamical setting, doing this inference technique, but only using current and past variables here. And so mathematically, I'm not going to get into the details of this very in depth, but the idea is just that we're going to have this approximate posterior over time steps conditioned on our observations, and that's going to be this product of these individual time steps, which are only conditioned on current and past terms, And if you're familiar with Kalman filtering at all, it's a very similar idea, what ends up popping out of this, where in Kalman filtering, it's in a linear Gaussian dynamical model. And the basic idea is that you infer the latent variable using your prediction and the error coming from that prediction. So in the latent space, this is how you would estimate the mean using exact inference for a Kalman filter, where you have some updated estimate of your mean, which is just a function of your predicted estimate. So you kind of initialize from your prior estimate. So this is the estimate in this white dot. And then you have this Kalman gain matrix, which is just this matrix that translates observations into latent. So this is kind of like the exact inference equivalent of an inference model. And then you have this prediction error, which is saying how off was this x hat, your prediction, from the true, oh, this should be an xt here, from the true observation that you're receiving. So it's a very similar idea of like, you have some prediction and then you update that prediction using a prediction error. And so the idea of this paper was basically, it's super simple. There was a little bit of math to actually show that you could actually do this in practice, but, or do this theoretically. But the idea is very similar, which is that each of these gray blocks here is showing one time step. And you're basically just saying, okay, and you have some prior prediction at your current time step. And then you, instead of just doing one update step as you would in a Kalman filter, you allow yourself to do multiple update steps to fully optimize at your current time step, your estimate, where you're kind of unrolling inference, multiple inference steps within each time step potentially. And that could be as few as one step, in which case you end up with something that looks very similar to a Kalman filter, but kind of a nonlinear generalization of that. So here we're just using an iterative inference model at each time step. So it's the same iterative inference model, I should say, but you're just applying it. You make a prediction at a time step, you update using your iterative inference model. And so the nice thing is that, like as I was kind of alluding to before, you have all these papers before that were looking at, okay, how do we do filtering inference using these kind of more direct encoder style models? And all of these were just custom designed by those particular researchers. They thought, okay, this would be a useful architecture for doing inference, but they weren't guided by kind of the structure of the model itself. Whereas this amortized variational filtering that we proposed is just a one size fits all solution to all of these models for filtering inference. And so again, you can kind of it's a bit harder in the dynamical setting to visualize this, but you can visualize kind of like what the prediction of the model would be here in like a time series setup. So you're predicting the output and then you're updating, and now you have something that more resembles the observation that you're seeing. So you're not capturing all of like the high frequency components here, but you're capturing most of it. And then you can also look again at like improvement over, training with more inference iterations. So here, the more you train, the better you do on this objective. The more inference iterations you train with, the better you do. And here it's showing for one particular model trained with 8 inference iterations, you see that over inference iteration it is learning to improve at successive time steps slightly, where it makes like large gains in the first few steps and then successively smaller gains throughout after that. And we kind of put this forward as just like, here's the technique. It matches or beats all of these custom designed inference techniques across a variety of data sets, from speech to video to music data sets. And yeah, it was kind of put forward as this kind of like, here's a baseline technique. If you don't know what else to try, use this just to sanity check what you're dealing with. Although I will say that, there's kind of some conceptual simplicity to these direct encoders that it's kind of hard to beat. So even though, you know, this is a one size fits all, performs quite well, it is maybe conceptually slightly more complicated in that you need to think about getting gradients and passing gradients instead of just observations into your inference network. So there, I will admit there's a slight increase in complexity there. Okay, so I wanted to finish this lecture with just a few closing remarks of kind of a few things I've seen and things I'm like excited about. And if anyone has any questions about anything so far, like feel free to stop me as well. But yeah, I wanted to kind of touch on a few things. Maybe it can help you in guiding your projects as well. So this is an interesting
Actually, Joe, I had a few questions just to help clarify things for the class. This does rely on having, if people want to use this in practice, this does seem to rely on having a pre-collected training set, and then some test example you observe at test time that you're doing inference on. There's an assumption that that test example is drawn from the same distribution as the training examples that you learn to do inference on. Is how true?
Yeah.
I mean, in some sense that's true theoretically because of IID assumptions, but how true do you think that is in practice?
I mean, I think it's true. Well, in all the data sets that we construct, that's usually true. But I actually think that somehow, like, inference should be, in a sense, general. So if you're really just dealing with gradients, then my philosophy, I guess, would be that it's better to let the inference network, don't worry about kind of regularizing or like making the inference network necessarily generalize, although there has been some investigation into generalization of inference networks. I think it's probably a better idea just to make sure that your generative model can generalize well. And then my thought would be that as long as your generative model can generalize well, then your gradient optimization procedure should be similar. So this is actually something that I've looked at recently where like in these kind of time series models, looking at learning some type of low-level preprocessor. And the motivation for that wasn't necessarily generalization, but I think like there's probably components that you can add to your model to make that generalize, and then by having your model generalize well, that should allow inference to generalize. Okay. But it's a very interesting point, and there's only been like maybe a few papers that have really looked at this aspect of generalization of inference networks. So I think that's, if any students are interested in looking at that, I think that's an interesting area as well. Okay, so there's a paper from last year's iClear, so just a year ago, looking at this issue of what they called lagging inference networks. So throughout this whole time, we kind of just thought about this thing of like, okay, we train the inference network, we train the generative network simultaneously, and we just kind of assume that it's all going to work out well. But if you think about it, the quality of the generative model depends on how good your inference model is. So there's actually maybe a case to be made that really you'd prefer to have an inference network that's kind of more optimized for your current, for your generative model relative to like how much you're optimizing your generative model. So the basic idea is that you'd like to have your inference network be providing you fully optimized estimates all the time. And you know, you can run into this issue where you have this negative feedback between inference and model learning. So you can kind of think of it almost as like a reinforcement learning problem where it's like, if you don't perform an optimal action at this turn, then you end up kind of learning the wrong thing, and then that kind of spirals out of control, and eventually you could end up at like a local minimum. Where you're not performing inference well, and you haven't learned a good model, and everything is just terrible. And so there's a paper in the variational inference setting. that local optimum corresponds to this setting where your approximate posterior is just equal to your prior. So your inference network is basically given up and says, I can't give you any information about this observation. Just go with your prior and let your generative model figure out what to do. And you especially run into this scenario when you have really flexible decoders, like a pixel CNN decoder. And this paper looked at this kind of issue where you can have these situations arise where if your inference network is kind of quote unquote lagging behind like the optimal estimate that your model would want, that can kind of like snowball over time. And you can end up with a model that's trained worse. You end up with, in this local minimum, or I guess local maximum in the variational inference case, where your approximate posterior is pretty close to your prior. You haven't really learned to extract any useful information from the data. And they kind of distinguish between these different cases of like, okay, is the issue that your inference model is collapsed, or is the problem that your model is collapsed, your generative model is collapsed, or have both of them collapsed? So kind of like the approximate posterior is equal to the prior is equal to the posterior. And so this is kind of like just an interesting way of thinking about it that I guess I hadn't fully thought about before, which is that we kind of tend to think of inference in this vacuum of like, oh, okay, we just perform inference and that's the end of the story. But really those inference estimates do affect your model. And so you have to be kind of cognizant of, is my inference network kind of shooting my model in the foot by providing bad estimates, and that's just kind of leading to this negative feedback. And then another thing that I have thought about a little bit recently, which I haven't really fully come to a conclusion on, which is that in these iterative settings, you have some added stochasticity. So because we're not using a direct encoding from our data to our estimate, again, we had like this ability to handle multiple maxima. So we could, have potentially even a more flexible inference procedure. So if you actually go in, and this is something I plotted just the other week, where you run inference multiple times. So this is, it's a bit hard to see, but on the top right is a legend that just shows, each of these colors is denoting a different seed of inference. So we performed inference 5 times here. And you see that none of these seeds perfectly overlap. And that's partially to do with the fact that, the optimization landscape might have multiple maxima to it. But it also could be just due to the fact that, we're using gradients to define our inference procedure. Gradients have noise in them because, by definition, we're only drawing a certain number of samples. And so you end up with some added noise if you think about like marginalizing over inference seeds. And so you see that, our individual estimates here are unimodal Gaussians. But if you marginalize over inference seeds, which is kind of effectively what you're doing when you're training a model, you end up with these multimodal estimates of this latent variable. And so that could have some beneficial effects. So that could say, okay, now you can explore the latent landscape a bit better. But specifically in my work, I've seen that actually this also results in having, because you're only running one inference seed, usually, you end up with higher variance gradients for your optimizer, for your model, for everything. And so it's kind of a mixed bag as to whether this added noise is helpful or harmful. And I think it's going to depend on the problem, going to depend on like kind of, the inherent structure of your model. But this is just some like added thing to think about that you wouldn't necessarily think about initially. So that's kind of an interesting side effect that I hadn't really thought of before. Another aspect is just, I really have brushed all of these details under the rug, but there are a lot of tricks to actually getting these things to work well. And I'll be the first to admit it. Like when I was trying to get iterative inference working, I basically, if you look at the code, there's like a laundry list of different setups to try. And a lot of those came from looking at previous papers where they did different things to scale the inputs to the models in certain ways. They made it recurrent or they didn't make it recurrent. And if you look through all the papers that are out there, there's not so many papers, but there's enough to see that, there's a lot of different tricks that people have developed in terms of like, okay, let's input as another input to the optimizer, let's put the iteration that we're currently at, or let's put in like some exponential weighting of previous gradients that we've put into the model. Let's take a log of the inputs, let's layer normalize the inputs, have the output be just a residual mapping or a gated mapping, more like an LSTM kind of a gate. There's a lot of tricks to it. And I think we're still at the point where like getting these things to work is still very much an empirical question. And I think specifically in this kind of like learning to learn or learning to infer kind of settings, I think maybe it's more settled in the meta learning for kind of like multiple tasks domain, but I think there's still a lot of theory that's lacking, and it would be interesting to see what, if any, kind of general theories we can draw out of how these models should be set up in some way. I'm not sure that it's possible, but it would be interesting to see. And then the thing that I've been looking at recently is, so if you're thinking, okay, generative modeling is great, but it's not really that interesting, I'm more interested in reinforcement learning. What blew my mind was learning that you can actually cast reinforcement learning as this inference problem. So you can, if you think reinforcement learning is super tough, like I'll never understand it, you can use a lot of the same techniques, and it's really a very beautiful kind of connection that exists. And so if you're interested, I would definitely recommend looking at this paper by Sergey Levin from 2018. But I'll just walk you through basically the setup, which is that we have here this type of computational graph where this node out here is our reward. And what we're really trying to do is maximize the likelihood of being optimal, which corresponds to this reward term in the objective. What we're trying to estimate, our approximate posterior, so our kind of latent space, is this action space. And what we're trying to estimate is a policy, which allows us to maximize the likelihood of being optimal or getting high reward. And kind of a stable way of doing that is by having some prior over what action to take. And so you have another term in here, this KL term, which you find in things like TRPO and PPO. But if your prior is uniform, then you end up with these max entropy formulations like soft actor critic, or these deep energy-based policies, like soft Q learning. And then finally down here we have the state, which is also part of this this model here. So when I saw this, it was like, oh, okay, this makes reinforcement learning make so much more sense. It probably won't make sense to you initially. You have to kind of mull it over for a very long time. But the kind of aha moment is that when you look at reinforcement learning, these policy networks that people are using, even though it kind of goes back to the encoder kind of thing of like, people just said, okay, well, let's hook up an encoder network and hope that that works. Without really thinking about kind of what are the implicit assumptions, what is this encoder network actually trying to do? When you look at reinforcement learning from this angle, you realize that a policy network, what's here drawn with these dashed lines from these purple to blue dots, policy networks are a form of amortized optimization, which is this direct amortized optimization. So I think the interesting thing is that it opens up, from this perspective, it opens up a lot of these new kind of ways of attacking policy optimization within reinforcement learning, where you can now try out different inference techniques here, and that's what I've been looking at for the past year or so. And so that's something that I think is very interesting, and I'm hopeful that people in variational inference and kind of this meta optimization field that's been growing can help to improve the reinforcement learning approaches that are out there. So I think that's an interesting angle, if maybe too much for a student project, but if you have any interest in that, like, definitely happy to chat about it. And so that's all I have. Is there any questions or want me to go back through any of the slides? I'd be happy to.
Yeah, I had a few follow-up questions just to maybe just to foster a little bit of discussion. You know, the vanilla variational autoencoder is in some sense assumption free. It's just, but many people who work in scientific modeling, they have other structural assumptions that they want to bake into their generative model. And then there's a question of, can we do amortized optimization in those cases? So dynamics and hierarchical are sort of two simple cases, but are there any general tricks that you know of when thinking about how to bake more structural assumptions into these generative models that are perhaps amenable to amortized optimization?
Yeah, so I guess one idea, just go back real quick, is, and this kind of gets to this issue of like structured, here. So structured inference, structured models requiring structured inference. And so I guess one way, so you can build in structure through these different nodes within, like, having different variables that interact with each other within your model. But even within a variable, you can model covariance terms, you can model nonlinear dependencies. So it's not really necessarily about building in scientific structure here, but this idea of normalizing flows, the whole idea there really is just, how can we build structured approximate posteriors with this idea of these flow-based distributions. And the cool thing is that you can actually apply those not just to inference, but to your model as well. So usually at the output of these models, you'd have a factorized distribution, like a factorized Gaussian, factorized Bernoulli. But you can model dependence within dimensions as well there too, where you have either a flow-based model or something like this pixel CNN, where now, like, what the pixel CNN is really doing is allowing you to model structure within or between individual pixels within the image, rather than just outputting here are all the pixels at the exact same time. So that's one way. Yeah.
Actually, I guess one maybe general way that people in various scientific applications try to model data is that they know they have different types of data. So like if you look at your hierarchical diagram by Sunderby et al. In 2016, sometimes there's two different types of x's, like x and x prime, and maybe x prime feeds directly into Z2 and x feeds to Z1. And so in those cases, I guess all of the previous work, they use a single inference network. So like inference optimization is learned using a homogeneous network everywhere everywhere. But if people have very different forms of data and they know that they should, they should be encoded differently, can you imagine cases where it might make sense to use different inference networks for different part of the structured inference problem?
Yeah, possibly. I guess it depends on how specialized your model is. I could imagine, like, if you had for instance, like a model where you had some categorical variable that totally like gates one part of the model, yeah, you might want like a specialized inference model that kind of handles inference in one part of the model. I could imagine that, although, yeah, I think in practice, yeah, it remains to be seen. Actually, I think for most of the models people are using, they're kind of simple enough in the sense that one inference network will probably do the trick for everything. But I could imagine, like you could include categorical variables within your inference network as well. There's this technique of having these auxiliary variables within inference networks, and that could allow you to kind of specialize and selectively have an inference network for a particular problem.
Okay. Any other questions from the students? Okay, great. Thanks so much, Joe. And tune in next week for more learning to optimize.